All right. Well, welcome to wireless. We're going to talk about the role of Wi-Fi as a network access technology. We're going to talk about the network types, topologies, a little bit of the OSI model, which will be a regurgitation from your Network Plus class. We're going to talk a little bit about peer communication, encapsulation, and device addressing. All these are going to be a very fundamental scope of what you learn in your entire semester of Intro to Networks, or as we call networking now, right? Okay, what are the network types? There are more than this, but let's talk about LANs. What is a LAN environment? Well, this room is a LAN environment, local access or local area network, right? A bunch of computers collected, whether they connect through a hub, a bridge, a switch, right? So they can intermediate and enter in that same broadcast domain. We have wide area networks, which is a collection of LANs, if you will. It goes from one LAN to another. That's a WAN connection. Wide area network. So you think wide area network, what do you think of? You think of that big fishing net being thrown out in the sea and comes up with all these big fish, right?
Walmart.
Do what?
Walmart.
Walmart? Walmart has a WAN. Each store has its own LAN. They're all interconnected and they go to the distribution centers. As soon as you scan an item, it's already on the truck for tomorrow's delivery, right? Metropolitan area network. What would be a good illustration of a man? Downtown. The Wi-Fi network downtown, right? Could be. That would be more of a campus area network because of the buildings that are just right around it. Yeah, it would be really more of a CAN. A man would be stretching more in mileage than a CAN. CAN would be something what we'd have here on Rose State. Okay, a campus area network where each building is its separate LAN. They're all interconnected, so they're not a WAN, but they are actually a CAN. Okay, which is a campus area network. MAN would be like the wireless network downtown, where you have blocks upon blocks upon blocks of wireless signals. Now, I don't know if Oklahoma City does that, but I know several others, like Austin does that. Free Wi-Fi for anyone downtown Austin, Texas. Then you have PANs. Okay, what is a personal area network? How big?
From your cell phone to your laptop.
How many feet?
33.
33 feet. You know that because you were in my class last night and you were paying attention. PAN has now been redefined. It is a 33-foot Bluetooth range. Used to, prior to the recertification or reclassification of PAN, PAN used to be your personal body, no more than 8 feet around you. Okay, that's what it used to be. Now they call that BAN, or body area network, so that your Bluetooth from your phone to your earpiece is considered a BAN, not a PAN. Even though it could be a PAN. Why? Because it's within 33 feet, right? But it's really considered within 8 feet is going to be considered a PAN. Or BAN, body area network. Now, if I'm doing computer to computer and I walk away from it, is really a body area network? No, it's a PAN, right? So they kind of overlap, but that's where they come up with. Let's see. I was going to make a pun on something, but I decided not to. A LAN, we just talked about it. Basically, it's just a small group or collection of computers all interspersed with a specific technology, whether it's the star, bus, basic framework, right? All connected to one center point device. More than likely, you consider it a star network because they all come to that one device. All right, it's no longer the bus. Bus would mean peer to peer to peer to peer. They're all on that one line. Okay. A wide area network is point to point or point to multi-point. How many of y'all have had intro to routing? So y'all know the point to point connections that you have on your WAN links, right? Your serial connections. That is what it's talking about. From that serial in to the other serial in, or whether it's octal or fiber coming into that module on that router. From router to router is what you're typically going to have for a WAN. Okay? So think about this. If I'm at home and I have 16 computers in my house, what do I have? If I have 16 computers connected to my WAP, what do I have? I have a LAN. The second it comes out of this to go to my cable, what is this connection? That is your WAN connection. Look on the back of any of your wireless modems. What does it say? WAN. Why? Because what is a WAN? It's a collection of LANs, right? So if I'm coming out my Cox modem, it's going back to their servers, which distributes out throughout their entire network, right? So that is how you define what a WAN is. A point-to-point link. Me to Lance, that's a point-to-point link. No one else in this conversation, no one else in this class will hear this conversation, but Lance and I will. Actually, you will, because my voice is Wi-Fi. But it connects 2 points together. Point to multi-point. I'm talking to Lance, who talks to Cameron. So can I talk to Cameron? Yes, because I got to go through Lance, and hopefully he's a really good interpreter. Okay, a MAN consists of a span that's from several blocks of buildings to entire cities that interconnect routes. Like I said, that's going to be your Wi-Fi in Austin, Texas. They're much larger than a local area network, a small collection of computers, but smaller than the WAN. So how do we define the internet? How would you define the internet?
WAN.
No, not just one, not just a WAN. The internet is a collection of WANs. Because I can have a WAN, but the only thing that you can see in that WAN is all the computers that are connected through those LANs to that WAN. But if I want to go back and talk to Mike's network, and he has his own WAN, I can have a point-to-point connection, but now we just only made a bigger WAN. When you have multiples, if everyone in here had their own WAN and we all talk together, now we have an internet, or a giant WAN. Yes, Derek?
So, like the military bases, would that be kind of like the internet, a collection of WANs?
Exactly. That's why it's called DARPANET. That's what it was built off of. Their own. They have a private. You have the internet, and then you have the private. But then they have the connection to where you can get into intranet sites, so you can actually see and communicate with the private network. Campus area networks. What is a campus area network? Just like I said, row state. Personal area network, again, within 33 feet of that device. Bus topology. Now let's talk a little bit about topologies. I already mentioned these, didn't I? Pretty good by just going off the top of it. Bus topology. I'm going to lay a Cat5 cable and I'm going to run it on down. Actually, it'll be a coaxial cable. But I'd run it on down, and what's going to happen?
I might hit the middle of it so that the last half of the group of people can't get the information.
You have that long cable, but it's broken off in segments. Now I can put a terminator here, but it'll connect to this computer. I have this computer. I'll have a terminator here. But on the ends, I have to have a terminator. Why?
50 ohms, so you can be able to test it.
No, it's so that my signal just doesn't degrade at the end of it. Because if I'm on A, it's got to go down here to come back. Or if I'm on B and I need to send it to A, it doesn't go this way because all the traffic goes this way. So it hits here and comes back.
Doesn't that also help you be able to troubleshoot it though?
Yes. Okay, ring topology. Normally in ring topologies, you don't see coaxial cable, you'll see fiber. How many of you have heard of the FIDI ring, right? Token rings. They're all fiber-based. What is a token ring? It just passes a token around from computer to computer, say you can talk next, you can talk next, you can talk next. You don't have anything to say, it goes to the next person, okay? That's what a FIDI ring does. And token ring. It passes a little device around. So from the file server, if computer A needed to get something, it's going to go, computer B, C, D, and E will all see that traffic before it gets to the server, which will then send it to A. So it takes a long time for you to get the request to the server if you're computer A. But then again, if you're computer E, it's quick to get to the server to get your request, but it takes forever to get the traffic because it has to go around the loop. All right? It's like your traffic circle. Don't ever get stuck on the inner circle of a traffic circle. Why? You will never get out, especially if you're in DC. Okay? Star topology, like we already talked about, it's a collection where you either have a switch or a hub. All the computers directly connect to it. They could go through the wall jack and come back in. But they'll connect into a device called a switch. That switch then connects to another switch or into a router, however they have it set up. That's your star topology. The reason being is because when you see that one device, everything spiders out from it, looks like a star. Right? Same thing with wireless. You're going to have that wireless access point. All the wireless devices connect to it, so that's a star. Does that make sense? A mesh topology. What is a mesh? It's multiple access points or multiple connections from each device, or in this case, each router. There are 3 connections off of each one of these to connect. So if one goes down, you still can connect to all the other routers. That's what mesh is. Think of when you hear the term mesh, fault tolerance, redundancy. Okay, that's where you're going to have it. If you have a partial mesh, this area one of these lines may be out. Okay, that could be a partial mesh. If it doesn't, you may, as long as you have 2 lines coming out of each router, you have a partial mesh. But some of these have 3, right? Because I can take it down, these 2 center sections. What do I have? I still have a mesh, right? Because there's 2 connections coming out. But is it going to be as redundant as this one? No. So we call these full mesh, and if you don't have it all the way, it's partial mesh. Maybe you have one device that's out by itself that only has 1 line going into the mesh, then you'd have it a partial mesh. Does that make sense? The scope or the boundary of the mesh only goes as far as your full, where everything is interconnected multiple times. Redundancy, fault tolerance. Same thing with wireless access points. As long as I have my access points all connecting in multiple paths, I have a wireless access point mesh. Again, I can have if I have one out here and it only connects to this one, I now have a partial mesh. But if I forget about it, I have a full mesh, right? Okay, how many of y'all are familiar with the OSI model, right? Please do not throw sausage pizza away. All right, physical, that sends your bit levels. Data link, what does that send? Frames. Network layer, this is where it starts to get important. Your network layer sends IP packets, right? So the protocol data unit is a packet. Why? Network also gives your IP addresses. The protocol that it uses is IP. So, network uses IP protocol, gives me my IP addresses, and it's a logical layer. All that makes sense, right? Now let's go up to the transport layer. What type of protocols reside on the transport layer? Just guess. TCP. Why? Transmission Control Protocol, right? So you have that transport part of it. Makes it easy to remember that it goes on there. Also, UDP. Those are going to be your connection or connectionless environments, right? TCP is connection oriented. That means I'm talking directly to Cameron. Cameron, we have our synchronous, right? Communication. If I do UDP, that means it's asynchronous. I just blurt it out, and hopefully Cameron gets it. You know your TV signals are all UDP, right? When you're streaming video, it's all UDP. Why? Because it doesn't matter what order the packets get there. If you drop a packet, you get the pixelization on your screen. Okay, those are drop packets. Can't tell you the number of times I had to tell Cox what they didn't know what the crap they were talking about, and then told them it was drop packets on the transport layer. They looked at me like I was an idiot. I don't understand it, you know. Hey, I'm telling you what the problem is. Go fix it. You know, it's UDP. It's going to have signaling issues, right? Session layer. This is where you get your connections, your secure shell, okay, your TLS. That kind of stuff comes on the session layer. And as you get up to application presentation, that's where you can get into your more application type environments, where you can get your FTP, your HTTP. All those protocols reside up in the application area. From session to application, they have one PDU, and it's called data. Because everything is created here. It gets encapsulated down at the transport layer. Transport layer says, okay, we're going to send it in TCP or UDP. Okay, that's all it does there. Then it goes down to the IP. Well, IP says, okay, it needs to go to this particular IP address. Fine. That's cool. Now we have a network to go to, right? We know what network it needs to go to by the IP address that's on there. Hopefully it is a live IP address and not a NATed IP address. Once it comes down to here, after we have our packet encapsulation, we go down to our frame level. I'm sorry, we segment the data at the transport layer to break it into smaller pieces so it can be sent down the pipe, okay? Once we have our IP address header on there, it comes to the data link layer. Now we get our physical address. What is the physical address of a system? The MAC address, right? So you have that MAC address that you put on this data link, and you have a trailer on there which uses your cycle redundancy check to make sure that everything is in sync from the application all the way down to the data link. What happens when it leaves the data link to go to the physical? It comes into bits, binary, ones and zeros. That's how it traverses over the medium. How many of y'all know what the medium is? It's the wire. It's how it or wireless. It's how it gets from point A to point B. That connection in between. Okay? And that's how it comes down. And then when it gets to the computer on the other end, if physical, it decrypts it back into a logical thing. Or when it gets to the next device, let's say it's going to a switch. The switch will take it up. Is it my MAC address anywhere on my routing table? Now, on the routing table, we have what we call an ARP table, right? Y'all have heard the term address resolution protocol that translates MAC addresses to IPs, right? Or IPs to, MAC addresses to computer names. Is it in any one of my address tables? No. If it's not, then it'll forward on to the next router. If it's a router, it goes up to the layer 3 to get the IP address so it knows how to get to the network. Once it finally gets down to that switch level on the opposite end, the switch reads it at data link level and says, okay, it's got to go to OBAE 074692, wherever that MAC address is. So it goes to that computer, okay? And sends it to physical bits. It adds that header back on there, sends it over there. Physical gets it, sends it all the way back up. The computer can read it, and voila, you got your information. That is how the OSI model works. Is there any questions on that? I know I went like 90 miles a minute on it, but this isn't the class to cover it. This is just giving you an understanding of it. Like I said, we already talked about the physical and the data link. This is where you're going to have a lot of your connections with the wireless transmissions, because they're going to go through the physical and the data link, right? And I'm not going to cover everything that I already covered. Like I said, here it comes down, gets encapsulated, goes back up, and gets de-encrypted. De-encapsulation. Pretty easy, right? Everyone understand these basic terminologies? Have I lost anyone yet? Okay. Like I said, I have my data. I come up here, put my header on at layer 4, go down to layer 3, get my IP packet header on there, come down to layer 2, have my layer 2 header, but you also have a CRC value that's right here. Then I get down to the physical layer, that adds my physical layer header, which transposes it into binary. I don't like how they do this because it's a little off. All right. Device addressing, our physical addresses are called MAC addresses, right? We just talked about that. IP addresses are logical addresses. So if I ask you to give me a logical structure of this room, what would you give me? You would give me 16 computers, you give me 16 computers, right? And just for abbreviation, I'm just going to do this. They all connect out. All right, to these 2 points. These 2 points come back to a switch. This switch is a 192.168.10.10/20. I'll just make it a 28 network. Well, actually, I didn't make it 27. Why did I make it a 28 network to start with? 28 network gives you 16 computers, right? But you take off your broadcasting, your network, that gives me 14 available. I couldn't have done it. So I had to go up to the 27, which gives me 32, take off the 2. Now I have 30 computers that I can put in this room. Obviously, there are 17 in this room. So guess what? That would be my IP, and that would be the logical structure for this. Now I can come in and say, all right, this will be, actually, 27 go by 32s. We're going to start on the 32 network. Okay? So this computer right here would be 32, or actually 33, because the network address is 32, right? 34, 35, 36, all the way down. Make sense? And that's how you do it. So how quick did I just subnet that in my head? Don't y'all wish y'all learned from me for subnetting, right, Cameron? No. I'm the subnet master. I'd love to do it in my head. It takes me about 26 seconds to subnet a network. At most. Those are the difficult ones. Y'all get to it one day. MAC address is basically like your physical house address, okay? 203 Peach Street, or Main Street, USA, okay? I'm the postman. I'm going to be delivering. Each address is unique, right? In the United States, you have your street, well, your street number, your street, your city, your state, and your zip, right? That makes everything unique. So that's how MAC address gets the packets, right? Just like the postman, they go to deliver it specifically to that MAC address. A logical address, I send it to this network, and hopefully that switch will then send it on. So I'm Oklahoma City Distro. I know that, hey, this IP range is over here off of this switch. I send it over to Midwest City. Midwest City then disperses it. Does that make sense? That's the difference between logical and physical. Logical gets you to the general area. Physical gets you to the specific. Now is it starting to make sense now how everything gets transpired over the networks? Is there any questions on this entire chapter? I know I just breezed by it in like 15 minutes for you, right? Yes, Derek.
I have a quick question. Okay. This is like Walmart.
Wasn't quick enough, no.
Lowe's. Okay. Like I used to work at Lowe's.
Right.
Okay. Now their server room would be on one corner of the building, and they would have to run fiber optics even to get to, say, the other corner of the building.
Because it's over
So,
300 feet, yes.
Would that be a WAN? Or
No, it'd still be a LAN.
Still
Yeah.
be a WAN, just extended.
If you're smart, you just put repeaters in between and use copper. But it'd save a lot of money. But if
Fiber optics.
yeah, it's still a LAN because until you leave that router of that building, anything inside of that router is considered a LAN. Now, if that the machine out there that is running fiber optic to doesn't go through that router, goes through a separate router, it still wouldn't be that computer would be on its own LAN, separate from the other computers that are in the building. But there's still LANs until you go outside. Just think of it, a WAN is defined by the connections to the routers. Once it gets to a router, you no longer have a WAN. Anything behind that router is a LAN. Or it could be a PAN or a BAN or whatever. Any other questions? No? Coolio. All right. Oh, man. 22 minutes. Broke my record. Okay. How many of y'all have taken your quiz? Let's do tonight, right? Guess what? The rest of you bring up D2L. And the reason I do this, I always do this on my first quiz, is I go over it with you in class. Let's go to 2643. Let's go to quizzes. I know I call it chapter test because it's really chapter quiz. It's the same thing, okay? The blank layer of the OSI model consists of bit level data streams in computer network hardware. What layer? Physical. So that's your answer. Okay? Our next question. A blank topology consists of multiple devices connected along a single shared medium with two defined endpoints. What did I draw up on the board? A bus network. The blank layer of the OSI model is responsible for organizing the bit level for data communications between devices on a network and detecting and correcting blank layer errors. Where did I say the CRC was? The cycle redundancy check checks us for errors, right? So what layer checks for those? No. No. Data link. The data link layer is the one that has the CRC check. Okay, it's the one that's going to check for errors of anything that is coming back up. So what's the layer below it? Physical layer. So it does in detecting and correcting physical layer errors. All right. The purpose of blank is to allow application layer data communication between two stations or a network using the lower layers as a support system. Encapsulation, because you encapsulate that traffic to send it down, right? It allows it to be able to talk to the next lower level. Y'all getting these? Be sure you spell them right.
I think I got one word misspelled.
Well, we'll see. The logical address of a network adapter is known as the media access control address. False! What is the logical address of a network adapter? The IP address. Good job. Y'all are smart. So that means I covered everything that needed to be covered in this class, didn't I? Well, at least in this chapter. So is there any questions on your chapter test?